Hello, this is Mrs. McBride speaking, and today I want to talk to you about heating and cooling curves. Now, why do we study heating and cooling curves? Well, we study heating and cooling curves for the same reason that we study phase diagrams, and that is to understand the flow of energy for each phase of a single substance. So we have a curve right here, and notice that on the y-axis, you measure temperature in the SI unit of degrees Celsius, and then on the x-axis we have time that is measured in the SI unit seconds. So as time progresses, notice how temperature is increasing. That means that as time progresses, you are moving up on the curve. The curve has a positive slope, so you are heating the substance. Now, if you look at this graph right here, as time progresses, temperature is now decreasing, which means you're moving down the curve. The curve has a negative slope, and the substance is now cooling. Looking at these two curves side by side, notice how they are very similar to one another. And that is because both of them are talking about the exact same substance, which is, in this case, water. So you're talking about water in this substance. So you really don't need to have a heating curve and a cooling curve separately. You could just look at one curve, such as the heating curve. So as time progresses and temperature is increasing, you are moving up, you're looking at the heating curve of it. But as time progresses and temperature is decreasing, you're moving down the curve, and that would be the cooling curve. Now, let's talk about on some aspects of reading a curve and how you actually read one. So you can tell from this particular curve that there are 5 distinct areas on this curve. So you've got Q1. The first diagonal line is a Q1, then you've got your plateau horizontal line, which is Q2, you've got your second diagonal line, Q3, second plateau, which is Q4, and then your third diagonal line, Q5. So these are the 5 distinct areas of your curve. Now, if you look at the first plateau line here, Q2, note this we call a phase change. This is where phase change occurs, so we call this phase change 1. What I mean by phase change is that at this particular area, this is where the substance changes phase. If you were talking about the heating curve, the substance will melt. If you're talking about the cooling curve, the substance will freeze. Notice also how the temperature does not change. Because the temperature does not change, or the temperature is constant, in this case it is 0, you would also say that the kinetic energy does not change. There's a lot more potential energy present. Now, looking at the second plateau or the second horizontal line, same thing is happening. This is called phase change 2, and when you were talking about the heating curve, we say that the substance is going through vaporization. If we're talking about the cooling curve, then we say that the substance is going through condensation. Once again, notice how the temperature does not change here. It remains steady at 100 degrees Celsius. So if the temperature remains steady, then the kinetic energy is not present. That means kinetic energy is either constant or is not there. And, well, kinetic energy is just constant. And there is a lot more potential energy that is present in the system at this particular moment. Now, if we look at the first diagonal line right here, right next to your y-axis, notice that this first diagonal line, we call this is the first state of matter, and we say that this is where the state of solid is occurring. The second diagonal line, the second state of matter is occurring, which is a liquid, and then you have your third diagonal line where the third state of matter is occurring, which is a gas. At the first diagonal line for the state of solid, Notice how the temperature is changing. Because the temperature is changing, now we have kinetic energy present. And kinetic energy is also increasing in this case. And you would have very little potential energy that is present. The same is true right here when we look at for the liquid. Because there's such a high spike in the temperature, there is temperature that is changing, causing kinetic energy to be present, and very little potential energy to be present. The same is true right here for the gas phase, where because temperature is changing, you have change in kinetic energy, and kinetic energy is present with very little potential energy. Now, if you look at the size of this plateau versus the size of plateau at phase change number 2, notice that the plateau at phase change 2 is a lot longer than the plateau at phase change 1. And the reason being is because more energy is needed to allow a substance to go through vaporization or condensation. So let's talk about this. So you've got here solid. Remember that solids are more of a compact. The molecules and atoms of a solid are more compact. They're more rigid. They're hardly moving around. But when you get to this first phase change here, now this is where the molecules start changing formation. So the molecules are now, well, let's go back to the state of matter for solids here. There is kinetic energy, so these molecules are beginning to move. But it's over here when these molecules start reacting and changing formation due to that kinetic energy. And so these molecules are spreading out and they're beginning to move faster. One of the reasons why they're moving faster is now when they're changing formation, they are actually bumping into one another. So by the time you actually get to the liquid state, the molecules have actually moved completely in the formation of a liquid in this phase change 1 area. So when we get to phase change 2, these molecules now need to have a lot more energy because it is a greater change in formation going from a liquid to a gas. Remember that gases are further spread out and the molecules are moving a lot faster. So the molecules and atoms at phase change 2 need greater energy versus the molecules and atoms in phase change 1, where they're simply just spreading out a little bit, still in contact with each other and not moving as fast. So we see this length right here for phase change 2 being longer, indicating that more energy is needed versus phase change 1 where not so much energy is needed. Now also, because you are in a heating curve gaining energy, the molecules are spreading out, they're moving faster, the temperature, notice, is increasing. Because the temperature is increasing, now you've got kinetic energy that is also increasing each time. Because kinetic energy is increasing, temperature is increasing, energy needs to be put into the system to allow these molecules to change their formation. So we say that the heat flow in this case is positive, and we would say that this is an endothermic reaction for a heating curve. On the other hand, if we are talking about a cooling curve, now the temperature is beginning to drop in a cooling curve, so kinetic energy in this case is beginning to decrease. Energy is really not needed because the molecules are going from a gas state of matter to more of a solid state of matter where they're coming together. So energy is being released. So the heat flow in that case would be a negative, And we would say for a cooling curve, that would be an exothermic reaction. Now, if you look at this, you can tell the substance that is being discussed in a heating or cooling curve. The areas that you need to look at to identify the substance is right here, the first phase change, and then the second phase change. The first phase change, we call this the freezing point, and the second phase change, we call this the boiling point. So notice here for this substance, the freezing point happens to be at 0 degrees Celsius. And right here for the second phase change, we would say that this is the temperature or the boiling point happens to be at 100 degrees Celsius. So there's only one substance that really has this characteristics where the freezing or the melting point happens to be at 0 degrees Celsius, and then the boiling point happens to be at 100 degrees Celsius, and that would be water. For that reason, this is the water heating curve. So if we're looking at other substances, we can identify other substances. So if you look at this very quickly, looking at the two curves right here, you know exactly what the second curve is. You can identify the substance because it is at 0 degrees Celsius is where the first plateau goes, and then the second plateau is at 100 degrees Celsius. So you can quickly identify this as a heating curve of water. But the second one is a little bit more difficult because now the second one, if you look at this, the first phase change is occurring at negative 114.1 degrees Celsius. And then the second phase change is occurring at 78.37 degrees Celsius. So that's something that you don't know off the top of your head. You would need to go and look up this information. But when you do, you realize that the substance that they are talking about, or the substance that this curve is actually indicating, is ethanol. So this is the heating curve of ethanol. So hopefully this helped you understand how to read a heating curve and how to use it to identify your substance.